Hello everyone, welcome to today's quantum space-time seminar. Today we are very happy to have Mr. Smolkin from Hebrew University, and he's going to tell us about the persistent order in CFT. Over to you, Misha.
Okay, well, let me just share screen. You can see it right now, right?
Yes.
Okay, good. So first of all, thank you very much for inviting me. It's certainly a pleasure to be in Tata, even though it is remote seminar, but still it's my first time, so I'm excited. So I'll share with you some results about persistent order and conformal field theories. So first, let me just mention my collaborators. So the whole presentation is based on a number of works that was done in collaboration with number of people. So this group is from Hebrew University, Noam Hai, Shumyadip Chaduri, and Ritam Sinha, who are our postdocs, and I guess you know them very well, and Eliezer Rabinovich, and two people from US, Anatoly Demarsky from University of Kentucky, Zorko Margotsky, and his student Changha Hoi from Stony Brook. So let me just start from telling you what we are going to discuss today. So it's so the whole talk rests on this wide perception that we always say to students and researchers that while global symmetries can be broken at low temperatures or at zero temperature, all the symmetries, global symmetries, I'm talking about global symmetries today. So symmetries are restored in a thermal state if you increase temperature to sufficiently high values. Okay, so so we are basically asking the following question: is it actually true in a UV complete, unitary, local, relativistic quantum field theory? And all these assumptions are crucial. I will argue that if you abandon one of them, but relativistic, so relativistic, I assume that this is true because obviously if you raise temperature to sufficiently high values, the theory is relativistic. So that's that's the basic assumption that I will not abandon. The other assumptions about UV completeness, unitarity, and locality are important. And if you just decide to remove one of them, you will see that you can answer this question. And basically, the answer is no, it's not true. So in other words, you can find examples that actually violate this perception. And truth to be said, that at the end I will not answer the full question. So in other words, I think there are still no counterexamples where you have UV complete, unitary, local, relativistic quantum field theory in, say, 4 dimensions or 3 dimensions. Okay, so let me let me start from just from something basic that we all learn from statistical physics from Landau and Lifshitz, so you can find it. So this is a precise quotation. So in the great majority of the known instances of phase transitions, the more symmetrical phase corresponds to higher temperatures. Just a moment, I have all these videos in front of me and I just can't see the screen. So the more symmetrical phase corresponds to higher temperatures and the less symmetrical one to lower temperatures. In particular, a transition of the second kind from an ordered to a disordered state always occurs with increasing temperature. But this is not a law of thermodynamics, and exceptions are possible. And as usual in Landau-Lifshitz, you also find a very concrete example. So this is the lower Curie point of Rochelle salt, below which the crystal is orthorhombic and above which it is monoclinic. So it's some kind of discrete symmetry. So you have richer symmetry at lower temperature, and then vice versa. So you have a given symmetry at lower temperature, and then you get a richer symmetry as you cross lower Curie point. So for those who are interested, this is a precise formula taken from Wikipedia. But as usual, if you just increase temperature sufficiently high, first of all, of course, if the temperature is too high, then your crystal melts, so you get a continuous group rather than discrete group, and in particular, you get eventually higher symmetry than at lower temperature. So another example. I think probably the first example in the context of quantum field theory was provided by Weinberg in the 70s. So where he constructed a UV incomplete 3+1 dimensional model. It's a closed cousin of phi to the 4th theory in 4 dimensions. This model, he just proves that this model exhibits symmetry non-restoration to all orders in the weak coupling. So just a very clear argument where he just shows that the symmetry breaks, and it doesn't matter how many orders in the weak coupling you take into account, the symmetry does not restore. And then many people who actually studied this model, they tried to find whether the symmetry restores if you consider strong coupling regime. And I think it's clear that in this model, well, again, it's not an exact proof probably. It depends on your standards, of course, but in this model, in the Weinberg's model, the symmetry is not restored all the way to Landau pole. Now, but these examples are, well, they are some kind of intermediate temperature examples. So in other words, you have to basically, if you go beyond the energies beyond the Landau pole, so you have to actually supplement it with some UV completion, and therefore it's just intermediate regime, like in Rochelle salt, and therefore we still have this question whether persistent symmetry breaking is possible. So, to answer this question, it is natural to consider conformal field theories, because such theories are UV complete, obviously, and represent UV end of the RG flow. So therefore, the question is clear. Let's take conformal field theory, find a temperature, and ask whether symmetry can take place. So this is a typical example. So usually we have a broken situation. This is a ferromagnet. You increase temperature sufficiently high, you go to yellow region where you have disordered phase. And the question is whether you can have an opposite situation where you increase temperature and you get actually into ordered phase. So in ADS CFT, there are no such examples. In other words, all examples that I know, and most recently they were constructed, there are a bunch of papers by Alex Buchel where he engineered various situations in the bulk. And in all these examples, the broken phase is subdominant in the canonical ensemble. So in other words, you do find some metastable vacuum, but the true vacuum is actually symmetric. Okay, so let me just briefly review the first example. The first example of conformal field theories which have some of its internal symmetries broken is the following. You take just 2 copies of the scalar field, so phi1 and phi2, and you add just phi quartic interaction. So it's phi I square, phi j square, and I and j runs from 1 to 2. So just 2 copies, 1 and 2. And so the fields phi1 and phi2 transform in the vector representation of the orthogonal group OM and OM minus n respectively. And in 3+1 dimensions, of course, this model is not interesting. It has just Gaussian fixed points, so it's trivial and there is nothing to explore. But one can go as usual below 3 dimensions. By D, I mean here just space. So you can go just a little bit below 3 dimensions, and in that dimension it has interacting Wilson-Fisher fixed point, and these CFTs we studied. So I will not describe this model in full generality. I will just review the simplest possible regime and mention what happens in general, because you probably did see it in other talks. So what happens? So we analyze it in various situations in the large n epsilon expansion, and by large n I mean take this n to be very large, but the ratio m over n is fixed. So this is a large n limit. So you can study it in various regimes. So we found that results match where the two regions overlap.
So, Misha, I didn't understand your. Could you go back to your Lagrangian, please? So ij run from 1 to 2. These are different kinds of fields, and then each of them is an n-component vector.
That's correct. So there are two. So what is written here? Take just the standard ON vector model. Now take another vector model and couple the two vector models. So phi1 and phi2. Okay, phi1 and phi2 separately. These are vector models. Except that now, because of you see G12 is not 0, G12 couples between the two vector models. So you have two vector models with different ranks, OM and ON minus M, and they are coupled by this off-diagonal element, G12.
Okay, thank you.
Okay, and we are interested, as usual, that's an a vector model. So we want to, the vector model simplifies the large n limit. I will just briefly remind why this simplification happens. So we want to take n to be very large, and we take n large and m large, and such that m over n is fixed. Okay, so that's the limit that we studied. Again, it's not the only limit that can be studied. One can just do the standard epsilon expansion. I will not review all the results. I will just mention them, but I will not actually show the detail, the calculations. But if some of you are interested in the details, I'll be happy to expand. Okay.
And sorry, at Gij equals 0, this model had an O capital N symmetry.
But that's true.
Okay, thank you. Yes.
So again, we take m large, such that m over n is fixed, and Jij is also fixed in this limit. Oh, sorry, Jij is also fixed. So here I just we factor it out 1 over n explicitly. Okay, so that's the limit. So two vector models coupled. That's the idea. And again, we go just a little bit below 3 dimensions. So actually, in the large n limit, you can actually study it in general dimension. But with an epsilon expansion, we just go a little bit below 3 dimensions. And then you can do the standard analysis, Wilson-Fisher-like analysis. So as I said, I will review just the large n at t equals 0 because it's very simple. It just really, as I will argue, it's super simple and super transparent. And finite t analysis is very similar, so I'll just mention the final results. Then I'll briefly discuss finite n corrections and switch to a different class of models. Okay. So let me start from large n. So large n, this is just a slide for those who are, I guess for all of you, it's something that is very well known. But let me just, for those who are less familiar, this slide explains why in the large n limit, vector models simplify. They essentially become free, and that motivates the approach that I will discuss in the next slide. So this is the standard single ON vector model. So just one field phi, it's a vector field here, no vector sign, but it's a vector field, and this is the standard, very well known, very well studied ON vector model, except that it's just Hamiltonian here. Now, in the large n limit, what one does typically, you can replace phi to the 4 interaction. So here you see phi to the 4 interaction, you replace by just a kind of mass term. You replace one of the phi square by the expectation value, okay, because in the large n it is justified. And what happens with this Hamiltonian, it becomes essentially a free field Hamiltonian. So this is what you see here. It's a free field Hamiltonian with effective mass, and the effective mass is just given by this expression. So this expression has many names. It just saddle point equation, Hartree-Fock approximation, self-consistency condition. So there are lots of numerous names to the same idea, that in the large n limit you can just package or hide interactions into the effective mass. And why this is a self-consistency condition? Because when you calculate this expectation value phi square, you have to use effective mass. So therefore, it's an implicit equation for mass. And this is why it is also called gap equation, because you solve it, you get mass for your particles in the large n limit. So since in the large n, effectively it becomes a free field theory, it justifies to look for the ground state in a Gaussian form. So this is, if the theory is free, we know that the vacuum state is just a Gaussian or a product of Gaussians for each k independent harmonic oscillators. So this is in momentum space. And in position space, this is a general form. It's just the same as above, except that here I also, so this D is just the standard Fourier transform of twice omega. Okay, this is this D, well, very standard, like product of harmonic oscillators. Now, and I remind you that D is only space here. So it's a ground state functional. Of course, for interacting theory, this is not true. It's not Gaussian. But in the large n, when n is large, I mean infinite, ground state should simplify and become Gaussian for the reason that I just explained. And here on top of, so this functional depends on a number of parameters. There are two fields, I remind you, phi 1 and phi 2. So you have two masses, M1 and M2, two masses that I still have to define these masses. And on top, there are the sigma parameters. So sigma is actually a center. So you have a Gaussian that is located in the space of fields. And it is centered around sigma 1, sigma 2. It has center somewhere. So if center is at the origin, so sigma equals 0, then of course the theory respects, the ground state respects all symmetries, because then there is no web for your fields. But if sigma happens to be away from the origin in the space of fields, that's the situation when the ground state breaks your symmetry. So the Hamiltonian is of course symmetric under the rotational group or the product of two. But if sigma is non-zero, one has to define it, then the ground state breaks the symmetry, and in that case you say that there is spontaneous symmetry breaking. Okay. So that's the motivation. So now here we have four parameters, two masses and two sigmas, because we have two fields. And the rest is just very trivial.
Could I ask probably a very stupid question? In going from the first line to the second line, I see that the Fourier transform of omega is replaced by the D inverse, but I'm not seeing where the sigma came from.
Yeah, you see, okay, I'll tell you. Here I don't have the sigma, because if you do Fourier transform, let's look at sigma squared for instance. So in that case, you see sigma squared, it's a constant, so it factors out. So you do integral over this D minus 1. Some constant. In other words, in momentum space, you have to add, I mean, to see the sigma here, you have to add some constants that I just absorbed in the
I see, thank you.
All the terms that are associated with my momentum space, they just become some constant in front of this exponent. So this is why I shifted to.
Sorry, I don't know if it is just me, but your voice, Misha, is getting low sometimes in between.
Sorry, log?
It becomes low. Your voice suddenly becomes low, and then again it comes back.
Sorry, probably I can't hear. Can you say, so what happens? You are commenting about the sigma?
No, your voice sometimes gets low. Your voice.
Abhijit is saying that your volume sometimes goes.
Volume. Sorry. I see. How is it now? Sorry. Is it okay now?
Yeah, it seems okay. Yeah.
Sorry. I just sorry. I thought you have a comment about physics. Sorry. Okay.
So I have a question.
Yeah,
so
sure.
Is this ground state a state of a state of the full The full 5-4 theory or the effective theory?
It's a ground state. So, you know, the ground state, it's an interacting theory. So it's a very complicated state, right? Functional.
Yeah.
Now, and this functional depends on various parameters of your theory, and n. I mean the n, this large, this n.
Yeah.
Or more precisely, this n and m, right?
Yeah.
So now, if you take this complicated functional, okay, and takes the limit n goes to infinity, okay. So this complicated functional will simplify and it will become Gaussian, okay. So for your full interacting theory, okay, in the large n limit, it will become Gaussian, because in this limit only, the theory becomes effectively free with appropriate mass, okay. So this is the slide, okay. So the Hamiltonian becomes effectively free with the Hamiltonian, except that the mass parameter has to be calculated and the mass depends on the coupling.
No, I'm just bothered by the fact that in the M effective square phi square theory, you don't have spontaneous symmetry breaking.
Where here in the Hamiltonian? It's okay, because this slide was no, it was a single ON model, and I just didn't care. It's true that I have, in principle, I could also incorporate it. It was just you know, a kind of I wanted just to remind why actually there is a simplification. Why the Hamiltonian? Why I look for the functional in the Gaussian form in the large n limit. That's it.
Okay.
I'm sorry, Misha, if you could go to the next slide once, please. If I look at, as you were saying, if I look at the term that was the sigma square in the second line, that involves the integral over x and integral over y. So those are the zero momentum modes, if you go back to momentum space. So it looks to me like the upper line has an extra term supported at zero momentum. That is not, that is phi I at k equals 0. That is sort of like a delta function term. Is that correct?
Yeah, you are absolutely right. As I said, when I wrote down this expression, I completely ignore. If you wish, I set sigma to 0, or I just did not account for them in the momentum space, because in position space I will be working in position space. It's more natural, I think.
I see. So this is sort of like the Bose-Condensate, like the macroscopic occupation of one state.
Yeah, indeed, that's true.
Okay, thank you.
Okay, so next, so again, but in this functional, so this is a functional in the upper line. So in this functional, as you see, I have, I have a number of free parameters so far, because I have a family of Gaussians. I have to specify sigmas, and I have to specify masses that are hidden in this D, okay? So how do we fix them? As usual, you know, we have to calculate, we take precise Hamiltonian. This is, I wrote it here. This is the exact Hamiltonian. We calculate expectation value of this Hamiltonian in this functional psi, just expectation value, and we minimize it. In general, it doesn't matter if the n is large or not. In general, this expectation value is greater than, of course, vacuum expectation value of the Hamiltonian or vacuum energy. But in the large n limit, so this is a variational principle that you're very well familiar with. But in the large n limit, since the theory becomes effectively free, only in the large n limit, this inequality is saturated. So in other words, in the large n limit, the sigmas and m's, they become actually exact answers. In the large n, again, 1 over n corrections, this is a separate story, and well, I will mention it a little bit. So that's it. So you just take the Hamiltonian, you evaluate its expectation value in this state psi, and that's an easy exercise because this is a Gaussian state. So it's just, you do the standard Wick's theorem, you compute, it's a simple calculation. It's an exercise with Gaussian, the simplest possible exercise in field theory that we so much like. So, so we do this exercise. So I will tell you what you get. So these two terms, pi's and gradient of phi. So of course, pi, it's in. So pi is just derivative, functional derivative with respect to phi. This is how you evaluate it. So these two terms I will call kinetic terms, and this is the potential term. So you evaluate it. So this is the final result for this kind of calculation. It's a simple, straightforward calculation. So this is the potential term. So the second term, the sum, this is the potential term with two sigmas here, and d here is not the d that it's related to the d in the previous slide, but this is the expression for these d's. And this is the kinetic, so you have two kinetic terms because there are two fields. So this is precise definition of this k, and this is the answer. And again, it's just a very straightforward calculation using Gaussian and Wick theorem, Gaussians. That's it. So this is what you get. So, well, and this x1 and x2 are these ratios, m over n and 1 minus x, or 1 minus m over n. So these are two x's. So now you have to just minimize it with respect to 4 parameters. But here the minimization is relatively simple because below 3 dimensions, if you look at k, below 3 dimensions, I'm sitting below 3 dimensions because I want to have this non-trivial fixed point. So, and again, I remind you, D is not space-time, it's only space. So below 3, this expression for K is manifestly positive. So, and the potential term, by definition, by stability requirement, it is manifestly positive. So therefore, if you find special points where W is 0, that's the global minimum of W. So how to get 0 value? Well, if you look at K and you want to make it 0, so since W, or this variational function, is sum of two positive terms, so if you want to get 0, you have to find special points where two terms, potential term and kinetic term, are separately 0. So for K, it's easy, just m equals 0. So just set m equals 0. And then you have to look for zeros of the potential term. So in principle, you would say, well, if Gij is strictly positive, definite, then presumably sigma is also should be also 0. But that's not the case, because it turns out, so let me just switch to the next slide. So you have to calculate fixed points, right? Because we see that the Wilson-Fisher fixed point, so I still did not mention anything about how you calculate it, but you have to calculate the values of the fixed points. Now, the value of the fixed point, as you know, if you are not close to 3 or to 3 plus 1 dimensions, well, it's a strongly coupled theory, and finding fixed points is not that trivial. But if you are sufficiently close to 3 dimensions, in that case, you have a crank to compute, to turn it and compute, calculate fixed points using the standard, calculation of the beta functions, etc., epsilon expansion, if you wish. So if you do it, I remind you that we are still in the larger limit when n is infinity. So what you find, if you just calculate your beta functions in this limit, you find that actually the beta functions, you have here 3 beta functions because you have G11, G22, and G12. So so 3 beta functions, 3 unknowns, you set all beta functions to 0, you would expect to find just, isolated set of points. But it turns out that in this limit, beta functions are not independent, so there is degeneracy. And therefore, you get actually a line of fixed point, or a conformal manifold. It has topologically, it's just a circle. Well, actually, it's a circle. And this is the parameterization of the circle. It's not that important at this point. To just notice that the determinant of the couplings, of the critical couplings, vanishes. in the larger limit. And this is, and there are fixed points on this circle where G12, so determinant is 0, but G12, the coupling between two vector models is negative actually, okay, is negative. And for this point, for these points where G12 is negative, you find not just one solution, okay, a single solution, or you find a line of solutions. So this is the line. So as I said, you set M to 0 to just to make sure that kinetic contribution of the kinetic term vanishes, and then you look for the 0 of the potential. And since the potential is degenerate, determinant of the matrix of couplings is 0, you get a line. Note that if sign of G12, this is the off-diagonal coupling between the two vector models, if the sign is positive plus here, so +1, so then actually you get only one solution, sigma, because sigma 1 square and sigma 2 square must be positive, so you will get just one solution, 0, and that means you don't have symmetry breaking. But if there is a fixed point, and there are such fixed points with negative G12, so if the sign here is minus, then here is plus, so you get actually a line. So you get, again, it's a 0 temperature calculation, so you get the moduli space of vacua is a straight line emanating from the origin. So I will present a kind of picture now, but how the above story is modified at finite temperature. You actually do essentially, you repeat the same steps as at 0 temperature, except that now you put your theory, you just do calculations on a thermal cylinder. It's still a Gaussian theory. Except...
Sorry, Misha, to get in my head, what can you sort of describe this fixed line again? What parameter varies along this line? So
yeah, so you can, so you see, so let me just maybe right. So you have G11, G22, and G12. Okay. So roughly, so you get a kind of circle here. Okay, so you can, so here, for instance, you see this is the parameterization of, you have a plane and determinant of G intersect, so you have to find intersection. So you have 3 parameters and 2 equations. So this is why you get a line. Okay,
right.
so you can.
This is for the conformal theory at the moment, right?
That's right. That's right. That's a conformal theory, and this is a conformal manifold. So for each point on this line, you get a CFT.
For each point, you get a CFT. Okay. Now let's say we fix all the G's to be somewhere on this manifold, and then we turn on our quartic coupling. You say that has with at fixed G's, it has a one-line solution, one parameter solution for vacua. Is that right?
Correct.
Okay, and this one parameter solution for vacua, can I think of it as being labeled by phi1 squared by phi2 squared? The ratio?
Yes, because let me just show you the picture. I have probably just. Well, I ignore it now. Okay.
I thought the G11, G22 had to do with the quartic couplings, right? I mean, they are the couplings of the quartic terms.
That's correct. But I'm saying that, so this is a space of quartic couplings, G11, G22, and G12. And but what Shiraz says is that for each choice, if you take a point on this line, so you choose a particular set of quartic couplings, so you get a CFT, and for each such CFT, you get a line. Here is a blue line. Well, not just a moment. So this blue line here. This blue line here. Okay. This is the line in the space of field. So you chose a theory already. So you chose some values of the quartic coupling, a value for the quartic coupling. So you chose a CFT, and for such a CFT, you now ask how the effective potential looks like. okay, for this system. And the claim is that the effective potential has a line, has a flat direction.
And the flat direction is explained by scale invariance, because if you choose some vacuum and then you scale it, you will also get a new vacuum.
But let's say, for instance, if you didn't have a situation with spontaneous symmetry breaking, say you don't have a spontaneous symmetry breaking, in that case, you would have a unique vacuum at 0, and that's it.
Correct.
Right?
Correct. So if you have some zero value of phi1 and phi2, then you scale it, it remains 0.
Right.
If you have any non-zero value, then the scalings of those will also be back.
That's
Okay, thank you. Now I understand. Thank you.
right. So here it's just a lot. So oh, probably my mouse right now to better from there. Sorry. So here at 0 temperature we have just a line that starts from the origin. Again, it's a large n so far. I will comment about finite n. So it's so you start at the origin and you get a line. And if you choose a vacuum that is away from the origin, this is a situation when you break scale invariance, of course, because now you introduce a scale, and you also break orthogonal groups On and On minus m. They are broken, and of course, and you can actually do the analysis and find all the particle spectrum which is consistent with Goldstone theorem. So gigaton, for instance, and all kinds of Goldstone particles associated with breaking of orthogonal groups. Now at finite temperature, so this is 0 temperature, so I described the full calculations. It's very relatively short and straightforward. Finite temperature calculation is very similar, except that you do this on a thermal cylinder, so you have all these Matsubara frequencies, etc. So you do this analysis again, you calculate the effective potential, variational functional, you just vary it, blah, blah, blah. And what you find that instead of line that you got at the 0 temperature, so this line is deformed into a what happens? I don't see mouse now. Something happened with my mouse. Sorry. Hello?
We can hear you.
You can hear, but something, I don't know, my computer's stuck. Very unfortunate.
We can't see your cursor. It would be helpful if you could see your cursor.
Yeah, that's true. This, but I'm saying that my computer is now stuck for some reason. So you can see me and you can hear me, but I can't switch slides. I can't do anything.
Maybe try again, closing and opening the program.
That's, you see, do you hear this kind of
yeah, but with the mouse, if you click on it, maybe
just stuck. That's just time it happens to me. Let's see. Oh. Let me. I apologize. I just lost control over this presentation. More. Can I just leave meeting and join it again? I apologize.
yeah, yeah.
Let me, because nothing works for some reason. I even can't leave meeting now. You see, I do leave meeting. I apologize again. So let me share the presentation. Okay. Okay, so this is the picture. So as I said, so at final temperature, the line is deformed into this curve. So this curve becomes just a hyperbola. And what is important here is that, okay, now you have to address your calculations with 1/n corrections. But in fact, even from the larger analysis, you can immediately see that it doesn't matter which one of these vacua survives 1/n corrections, because none of them belongs to the origin. And that means that at finite temperature, so at zero temperature, you still have a possibility to start from a CFT that respects the full global symmetry. So I mean, the vacuum sits at the origin. But once you turn on temperature, the vacuum becomes one. At finite temperature, your vacuum or your state becomes one of the states on this hyperbola, and doesn't matter which one of them. It for sure it breaks the global group, the global orthogonal group or product of two groups. So this is what you learn from large N. But of course, you have to understand. One has to still understand what actually survives 1/n corrections.
Sorry, could I ask? I was understanding the existence of this flat direction, this blue curve on the left, as a consequence of a broken symmetry, namely scalar directions. But from that point of view, the fact that there continues to be a flat direction at finite temperature is extremely surprising, right?
I agree. So therefore, it's not, well, if you ask what is the generator that shifts you between this vacuum on the hyperbola, I don't know. Actually, we did not study it, or we didn't understand it. So it's some combination. I don't know, of some generators that left unbroken, but I don't know what it is exactly.
And I suppose you'll tell us about this, but is the existence of this flat line a large N artifact, or do you expect it to be?
That's an artifact of, well, it depends on your standards. Some people call it a feature of large N. So, but I agree that realistic theories have finite N, and therefore, from this perspective, it's an artifact. And indeed, for finite N, all these lines disappear. So remember, you have a line in the space of couplings, and for each point on this line, on the conformal manifold, you have a line in the space of fields. Okay, so that all these features disappear. So let me, since I just running out of time, I would like to.
Sorry, please don't worry about time. We're very flexible about time.
Okay, very good, very good.
Okay.
But please,
could I?
But if some of you, I mean, if you feel like I abuse, okay, your time, so kind of your you know your flexibility. So please tell me, okay, and I will stop. But don't worry, I will try not to run too much.
Sorry, and the blue line. I suppose it's a question of which fixed point survives, but the blue line could in principle be an exact feature even at finite N, right? Because it's a consequence of symmetry.
Well, in fact, again, it all disappears. This feature of the flat directions, it disappears in this.
Okay, thank you.
It's all lifted. Okay, so
and the understanding is that in the second diagram, the understanding is that at zero temperature, the phi2 has a finite expectation value. Is that right?
At non-zero temperature.
At non-zero temperature. So,
this is,
what happens?
Yeah. So okay. So let me explain. So it's true that in principle, this hyperbola could. Let me use again annotate. So this hyperbola could be either this way or this way. Okay. It depends which rank is bigger. Remember, we have the rank. This is our group: ON cross ON minus M, right?
Yeah.
So this is, say, phi1, and this is phi2. So to get this picture, you have to have n minus m bigger than n. Okay.
Why is that? I thought.
Sorry, that capital N should be m, right?
Okay, because, okay, maybe I should write it. I take n to infinity and m, so.
The capital N should be m.
Sorry, my mistake. It should be, this should be m. Oh. This should be m, okay? And I take, sorry. So let me picture it. So I take m over n fixed, remember? So therefore I can write this gentleman as n times x1. So this is x1. And this gentleman here, I can write as n times x2, where x2 is 1 minus x1, okay? So now the question is which rank is bigger? N is large, x1 and x2 are fixed, or x1 is fixed, so their sum is 1. So now the question is which rank is bigger? If this rank is bigger, or the rank of phi 1 is bigger, okay? So if x1, so this picture, maybe I should switch color. I will not switch. So this situation here corresponds to the case when x1 is bigger than x2, okay? And the situation here corresponds to x2 bigger than x1, okay?
But the rank and the vacuum expression values, how are they related?
Because, you know, you see here, this expression here, you can ask how far this hyperbola crosses the line. So this of course, it has dimensions. So the dimensions are built from temperature, okay, temperature to appropriate power. But then there is a numerical coefficient here, some numerical coefficient here. This numerical coefficient depends on ranks, because if you go back, let me stop it. If you go back, you see the variational functional depends on this x1 and x2.
Okay.
Okay, so this is why, and the same happens with variational functional at finite temperature. And therefore, when you actually look for a solution for the vacuum or for the minima of the variational functional at finite temperature, this minima is fixed by this hyperbola, and the point where the hyperbola crosses the line is fixed by, is determined by temperature, just based on dimensional analysis, and the numerical coefficient depends on x1 and x2.
Okay.
So I just wanted to say that that both situations are possible. It depends which rank is bigger, and if you take equal rank, x1 equals x2, this is the case when you will get a line. Okay, so in other words, you start from hyperbola on one axis, and then imagine that you gradually increase x1. So your hyperbola at some point when x1 equals x2 degenerates into a line, and then it wraps around phi 1. Okay, so you have a family of hyperbolas that go like that, approach the origin. Sorry for my poor drawing skills. Then you get a line. This is the situation when x1 equals x2, and then when x2 becomes greater than x1, then hyperbola starts wrapping around phi 1. Okay.
Okay, so what is the upshot here? I mean, what are you trying to interpret?
So the upshot is the following. At zero temperature, if you ask what, now you turn on 1 over n corrections. Imagine, well, again, at zero temperature, you have two possibilities. Either you have a CFT vacuum, okay, or a vacuum that respects all symmetries, or you have a situation with broken symmetries, okay? So if you take one vacuum away from the origin, you will get broken scale invariance and broken global symmetry, ON cross ON, or OM cross ON minus M, I mean this symmetry, okay? Now, at finite temperature, probably I should just clear all drawings. So at finite temperature, if you consider situation with x1 different from x2, okay, so that means non-equal rank. For non-equal rank, your moduli space of vacuum does not cross the origin. Okay, it deforms into the hyperbola. This is what happens, and this is why at finite temperature it doesn't matter how your theory looks like at zero temperature. So imagine that you start from a CFT that respects all symmetries, scale invariance and global symmetry group. I mean this OM cross ON minus M. So all symmetries are respected. Now, if x1 is different from x2, if the ranks are not equal, then at finite temperature, your moduli space of vacuum does not cross the origin because it is necessarily a hyperbola. And therefore, symmetry will be necessarily broken. The global symmetry, I mean OM cross ON minus M. The scale symmetry is broken, that's not a surprise because you have temperature. So it is broken, that's fine. But global symmetry will be necessarily broken. And since it is broken at any temperature, since we are in a CFT, so it doesn't matter if you take a temperature to be high or low, as long as it is non-zero, the global symmetry will be broken, necessarily broken.
Yeah, so the upshot is that at any temperature, the symmetry is broken.
Correct.
Whereas in the left-hand side, at zero temperature, the symmetry is restored.
Well, at zero temperature, so in other words, you can have a situation where you start from a CFT, which respects all symmetries. Symmetry is not broken, okay? Completely symmetric situation. You turn on temperature and the orthogonal group breaks. Yeah. So finite temperature breaks the orthogonal group. Of course, it breaks explicitly scale invariance. This is okay because it's explicitly broken by scale, by temperature. But what is less intuitive, or if you wish surprising, is that the orthogonal, the global symmetry breaks at finite temperature, as long as x1 different from x2.
Yeah.
Okay. So again, this is just studies of large N, but then one can actually consider.
Sorry, Misha, are the axes on the second graph phi1 squared and phi2 squared? Or
no,
if you well, it's actually phi1, phi2. It's here it's phi1 and phi. It should be phi1, phi2, but in the case at zero temperature, it doesn't matter because phi1 is proportional to phi2. So if you square it, phi1 square is proportional to phi2 square. Here you need actually phi1 and phi2 because it's a hyperbola in the sense that you have something. Let me write it.
Oh, I see.
You have alpha phi1 square plus or minus, sorry, beta phi2 square equals some constant. Okay, that depends on temperature.
And is phi1 defined as the square root of the operator phi1 squared?
Right.
So I'm not understanding if phi1 squared and phi2 squared are both invariant under the global symmetry. So why does the fact that they have an expectation value imply that global symmetry is broken?
Well, because again, you have to choose one of the points here. It's like if you wish, like in the Mexican head. You also have a situation when everything is, the potential is has the symmetry, rotational symmetry, right? But then you pick one of the vacua.
But even if you were at the bottom of a potential in quantum mechanics, phi1 square will in general not be true. Because phi1 square is not the same as phi1, the whole thing square. Sorry, I'm asking something stupid, I know.
No. Why stupid? No, everything is stupid, but or smart. I don't know. Again, you're worried that I take. So why actually I associate phi1 with square root of phi1 square?
That's right. I was thinking that if you take you would want to show that there is some operator that violates the symmetry that has a non-zero expectation value.
So I calculate now effective potential. Okay, the effective potential is of course a function of phi1 square. Let me. Yes. Okay, maybe let us go back here. Let me just turn it off. So, I mean, these parameters, sigma, so phi1 and phi2, there are these parameters, these sigma parameters. So the potential depends on sigma square, but where sigma came from? It came from this form of the ground state, right? The sigma I and sigma j, whatever, sigma 1, sigma 2. This is the ground state functional, okay? Ground state functional. So I have sigma 1 and sigma 2, and that's the center of my ground state functional.
Yes.
Okay. So here, I think you agree that if I tell you that sigma is non-zero.
Yes, yes, I agree.
Okay, very good. So now I calculate explicitly my this W variational functional, and it depends on sigma 1 square and sigma 2 square this way. Okay. So this is what it is. And sigma 1 and sigma 2 here, I'm sorry, I apologize for the mess in the notation, but let me clear all drawings. But this phi 1 and phi 2 are sigma 1 and sigma 2. I'm just sigma 1 and sigma 2 here.
Yes.
So this is sigma 1 square and sigma 2 square. It's just the potential depends on sigma 1 square and sigma 2 square, but the fact that you have non-zero value for sigma means that you have a broken symmetry.
Okay, thank you. And in particular, it would mean that there's a Goldstone boson, right? You can check that.
Right.
I suppose.
Yeah, this is right. This is NGB. This is Nambu Goldstone.
Okay, thank you.
Boson. Okay. Okay, so let me just tell you what happens when you take finite rank correction. So remember, I told you that we have a circle of fixed points in the space of couplings, right? A kind of loop. So this loop actually disappears. Only isolated fixed points remain, and there is always one fixed point with negative G12, okay, which survives finite n corrections because it was essential that the off-diagonal element of the matrix of couplings is negative. Only then you get these lines of fixed points. Oh, sorry, lines of flat directions in the potential. So, so you do this analysis. You just account for 1/n corrections in your calculation of the beta function. This is of course possible and rather standard. And you check, and you find that for each fixed ratio m/n, one such fixed point survives, and only one vacuum survives. So in other words, this flat direction is lifted in once you account for 1/n corrections. So therefore, using the terminology of Shiraz, this is just a large n artifact. So in other so only one vacuum which survives on this hyperbola, and this vacuum corresponds to the vertex. This is the point where the hyperbola intersects one of the axes. Okay. So for non-equal rank, the lower rank group is broken. So in other words, as I told you that this hyperbola corresponds to the situation when phi 2 transforms under a lower rank group. So therefore, only lower rank group is broken, and for equal rank there is no symmetry breaking. So in other words, for equal rank, what happens is that you have a straight line in the large n limit at 0 temperature. You have a straight line at finite temperature. Once you turn on 1/n corrections, these straight lines disappear. You have only unique vacuum at 0 at the origin. So therefore, you have symmetric situation at 0 temperature. You turn on temperature, you stay in the symmetric situation. So to get symmetry breaking, you need to break equality between ranks. So this is what happens in this model. Now it has some setbacks. If you are, you can say the following. Well, what are the setbacks? It's so far it's in the fractional number of dimensions, obviously, and And so you can ask, okay, what happens when you take the small parameter epsilon when you approach 3 dimensions? And in 3 dimensions, I hope I mentioned it somewhere. So in 3 dimensions, so in other words, can you take the limit epsilon goes to 1? That's a central question. So, and you know that actually in 2+1 dimensions, or in 3-dimensional space-time, continuous symmetry cannot be broken in local theories. This is a famous Coleman, Hohenberg, Wagner, Mermin-Wagner theorem. So therefore, you do expect that as you approach integer dimension, there should be some difficulty to keep the symmetry broken. And what happens in practice, if you just check the value, so you see you have, the question is how far this point from the origin. So as I said, by dimension analysis, it is proportional to temperature to some power, but there is a numerical coefficient. And as you take dimension to 3, to 2, or d equals 2, or 2+1 dimensions, as you take the limit to 2+1 dimensions, or epsilon equals 1, so this point escapes to infinity. Okay, so everything is shifted to infinity. However, if instead of considering continuous groups, you just take the situation when one of the groups is O1. So in other words, you just study the situation in the large n limit, but in the situation when one of the groups is O1 cross On, such a situation. In that case, so this O1 is just that Z2. Okay, this is Z2. So you just take vector model coupled to just a single scalar, to Ising model, if you wish, vector model coupled to Ising. So in that, and you study do large n analysis. So you will find again the same situation, same moduli space of vacua that disappear, conformal manifold, everything exists also in this case, and everything disappears as you take 1/n corrections. But in that case, the limit epsilon goes to 1 is actually smooth. So this point does not escape to infinity. And therefore, we claim that this is a candidate for symmetry, for a local unitary theory, UV complete in 2+1 dimensions, where discrete symmetry can be broken, except we cannot show it directly in 2+1 dimensions. So it strongly relies on your belief in epsilon goes to 1 limit. Again, in the case of continuous groups, continuous global symmetry, you do see singularity as you approach 2+1. In the case of Z2 coupled to vector model, you don't see it. But again, doing calculations directly in 2+1 or showing that the symmetry is broken, we didn't succeed. We couldn't show it directly in 2+1 dimension. So that's a candidate. We call it a candidate.
What is the problem of with doing larger n directly in 2+1 dimensions?
Well, the question is, what's the fixed? You see, everything relies strongly on the values of the fixed points, right?
Yes.
So eventually you have to tell me what's the fixed point, because you do calculation of effective potential. What is the fixed point? So,
yes.
So usually we calculate, you know how to calculate perturbative fixed points, and this is close to 3, equals 3 or 3+1. And directly, to do it directly in 2+1, I don't know how to do it.
But at large n, I think even though it's not far away, you probably could compute.
In the large n, okay, I will tell you what you can do in the large n in a moment. But again, usually in the large n, you do not really calculate values of the fixed points, right? You just do some kind of critical models, critical large n models. You don't really, at least I don't know if you calculate.
You can go to one subleading order and then get sometimes fixed point. But I can ask you later. Please go on.
Yeah, all I can tell you that we didn't know how to do it. Okay. I will tell you for myself. I didn't know how to do it.
I have a question. Like, when you have, say, vacuum expectation values, you usually have a single component of the entire field taking a certain vacuum expectation. You don't have the full, I mean, the point of Shiraz was that what does it mean to take the square root of the square of the entire set of
Again, I
points?
did take, again, okay, just a little bit, my terminology was a little bit misleading. I didn't take really square root. What I did do, look, again, let me just repeat. So the whole calculation rests on this form of the vacuum functional, okay? So I have to see here there are no square roots, it's just sigma.
No, so you have to choose one of them, right? I mean, or else how are you going to, what does that graph mean then? I mean, if you have multiple sigmas, you'll have a multi-dimensional plot.
You mean which one? So
if you have multiple sigma i's,
but again, by rotational, you know, the original theory is rotationally invariant, right? So it's as usual. Call this direction, whatever direction you pick, call it I don't know, call it phi 1 or whatever, but direction 1.
Usually when spontaneous symmetry breakdown takes place, one of them takes a vacuum expectation value. The others are usually left, so as far as I understand.
So again, let's see. So say in the case of OM, yeah. OM is negative mass. So you have such a potential, right? With negative mass. Just single OM vector model.
Yeah.
With negative mass. Right, this is how the potential look like, right? So which one of them you will get a manifold, right, of vacua, right?
Yeah. So when the ON model say gets broken to ON minus ones, for instance.
That's correct. This is what happens here. That's true.
Yeah. Exactly. So then one of them takes a vacuum expression value, and the rest of them are left alone.
Right, I'm talking, that's true. This is the sigma here corresponds to one of them. We just do not specify.
Yeah, okay, fine. And another thing is that when you are saying, can you go to that ultimate slide, which we were discussing before?
Yes, sure. This one or?
Yeah, that one. So the point was that at finite temperature, your motivation was to show that at finite temperature, the symmetry gets restored in some sense. I mean,
no. No. I claim that at finite temperature, the symmetry is necessarily broken. That's the claim. The question, what's the pattern of the symmetry breaking? That's a separate question, but because it depends where exactly on the hyperbola you are sitting. But all I'm saying is that since the flood direction or the minimum, global minimum of the potential does not, or this line of global minima does not cross the origin, it means that the symmetry will be broken because phi 1, the sigma, okay, calling them sigma 1 and sigma 2, one of them will be necessarily non-zero.
Yeah, so usually when at finite temperature, the symmetry, okay, at finite temperature, you are saying that the symmetry usually gets restored. That's what you're saying. Correct. So here it's showing that it's getting broken. That's what you're saying.
Exactly. That's okay. Exactly the opposite. Exactly okay. The opposite. Okay. So you start with symmetric situation at zero temperature. You start with the CFT, which is symmetric at zero temperature. You turn on temperature and the symmetry breaks. Okay, that's opposite. This is why it is counterintuitive. Exactly.
Yeah.
Okay, and in the CFT, it doesn't matter. All temperatures are very much the same, right? I mean, if it is broken at any non-zero temperature, it will be broken for all temperatures. Okay. Yes, of course.
Hi, so this statement was that like in CFT you break it at one temperature and it's broken at all temperature, relied on the fact that there's no other scale, right? So if you have a slight chemical potential or something, do things change drastically?
So I apologize, I just couldn't hear you. You say that.
So I'm saying if you add a slight chemical potential, does that conclusion drastically change?
If you have, so you're asking if the calculation changes. If you what do you have on what kind of?
If you have a small chemical potential, I'm asking.
If you have a chemical potential, I think okay. So I think you can do this calculation. So you can add. You mean you want to add charges, I guess, and you ask
right.
You add charges, whether the calculation gets dramatically more complicated. So the answer is no. It will be a little bit. Well, you will have some extra. We will have to compute a little bit more, but it is doable. In the large N, for sure, that's no question.
But now there's a play of different scales and so on, right?
Well, you see, again, we were interested to consider canonical ensembles because there are some examples. There are not many, but there are examples with chemical potentials when you have charge in your system and then the symmetry breaks. Well, except that I think these examples are non-unitary because people study their kind of imaginary or complex chemical potentials. But the punchline is that there are studies of, not in these models, but there are studies of chemical grand canonical ensembles or symmetry breaking in the grand canonical ensemble. So there are some results. But I'm not aware of results in this kind of charged models.
Okay, thanks.
Okay, so right. So I told it. Okay, so now. So one can ask, okay, what happens? So that's related to the point that Shiraz raised. What happens if you just do large N, the typical large N technique? There are nice large N techniques which are not do not rest on a particular dimension. So you can do this 1/n analysis using these techniques. And so what we did with Ritam, Norm, and Eliezer. So we studied this situation. We were interested to understand what happens with conformal manifold. So what you see is that when you turn on, if you sit close to 3 dimensions, 3 space dimensions, no time, then you have this conformal manifold that disappears as you turn on 1/n corrections. So we raise the question whether this is true so if you take epsilon of order 1, so you go a little bit deeper or closer to d equals 3, whether one can actually preserve conformal manifold. So so we studied. We didn't bother about value of epsilon. We just studied large N, did some large N calculations using 1/n techniques. And how it works, you identify in the large N limit, you identify exactly marginal operator, which is associated with the conformal manifold. And then you basically calculate anomalous dimension of this operator. This is what you should do. So we did it. So it's a bit technical. So I will just show you one slide. So this is a slide you take. So these crosses here correspond to exactly marginal operator in the large N limit, when in the N equals infinity limit. And these diagrams represent kind of 1/n correction to the 2-point function. So such calculations were done in the literature in the context of standard ON vector model. Well, there you don't have conformal manifold, but people just calculated all kinds of anomalous dimensions. So here we do the same for this model that also has a name. It's a biconical model. So we did this calculation. We studied the anomalous dimension. So it's a bit technical. These are the diagrams and all kinds. So this solid line correspond to phi's, and this dashed and the wavy lines correspond to the so-called Hubbard-Stratonovich fields. It doesn't matter. This is just, you know, so that you have a picture in mind what kind of diagrams you have to compute to account for 1/n effects. And this is the anomalous dimensions that we got. This is the plot of this anomalous dimension. So you see in general it is non-zero, but somehow it's surprisingly, it has a zero value somewhere between 2 and 3 dimensions. This is space-time dimensions between 2 and 3. So in other words, it crosses the zero axis. So therefore, in this somewhere in between 2 and 3, in the large n limit, you get back. I mean, your operator is exactly marginal, even at 1/n, and therefore, in principle, you might get a conformal manifold. That, of course, raises a question whether one can find, instead of taking n large, maybe you can find a critical n such that this point moves towards 3, but we don't know the answer, we didn't figure it out. It just was a little bit surprising that the sign is not well defined of the anomalous dimension. So in other words, it crosses the zero.
What is the exactly marginal operator? Which operator is this?
It's well, it's, if you wish, it's some combination of 5⁴ operators. Some combination of 5⁴ operators that shifts you along this line, because the line, this conformal manifold, lives in the space of quartic couplings. So therefore, the operator that moves you along this line, close to d=3, is related to combination of 5⁴ operators.
I see. Thank you.
Okay, it's true. I do not present these details because it will. You can, if you will be interested, of course, you can find everything in our paper. But I just gave you an idea what happens. So let me now switch to a different example. I just had to say that our example, if you stay in a fractional number of dimensions, you have a CFT. This is good. You have it's a relativistic, or if you wish, well, Euclidean theory. It respects rotations. Everything is good. So it is local. Everything is good. But you can raise the question whether it is unitary. In fractional number of dimensions, it is actually not necessarily unitary, because there is a nice work by Slava Rychkov and collaborators where they just studied the conventional, the standard Wilson-Fisher fixed point in fractional number of dimensions, and they engineer it even actually in free field theory. You can take just free field theory. So you can engineer in fractional number of dimensions, you can engineer special operators that have do not respect reflection positivity, or you wish the two-point function of these operators, even in free field theory, is not positive. Okay, so this is what they showed. These operators vanish when you sit in integer number of dimensions, and they are non-vanishing in fractional number of dimensions. And therefore, since you have an operator that has negative two-point function, that means you have negative normal states, and that means there is no unitarity. Okay, of course, it restores as you go back to integer number of dimensions. So therefore, if you remain in a fractional number of dimensions, you can say, okay, your theory is CFT, relativistic, blah, 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 but it is non-unitary. Okay, so so now the question whether one can construct a unitary theory. So this is what we did using the so-called long-range Ising model, or just generalized free fields. So in that case, you abandon locality. So you forget about locality. You study unitary, you study CFT, UV complete, relativistic, everything, all the nice features are preserved, but you abandon locality. Okay, so if you abandon locality, then you can engineer such a nice theory in integer number of dimensions. So here I will briefly describe, because I guess you're already tired. So first of all, just a big, just a short review of this long-range Ising. So this is a long-range Ising Hamiltonian. So you have the standardizing, except that now you allow your spins, not only nearest neighbors interaction, but all spins interact. And the strength of interaction goes as 1 over r to some power d plus sigma. So this model was studied by many, many people, including Dyson, that I forgot here. Throughout the years, and there are also recent results by Parisi and Slava and Miguel Paulos, many people. Maybe I didn't mention all of them, but there are lots of results about this long-range Ising. So in the limit, in the continuum limit, it has like short-range Ising model. It has second-order phase transition at a critical temperature. Now, if you take sigma, so D is number of space-time now dimensions. So this is space-time, but well, no space-time, it's only space because everything is Euclidean here. So if you take sigma below D over 2, then it's known that the critical point is a Gaussian theory described by a non-local action of this form. So you get, this is in the continuum limit, this is what you get. And but if you take sigma above D over 2, but below certain critical value, sigma star, so this is the plot here taken from one of the Slava's paper. If you take, so then you get the critical theory can be obtained by perturbing the above action. So you have this Gaussian action, so Gaussian theory, and you perturb it by a local quartic interaction. So you just add quartic interaction to this non-local Gaussian theory. Okay. So there is some. So this is the short-range Ising here. Here in between, you get this non-trivial long-range Ising model interacting. So it's a CFT and blah blah blah. Except that, of course, it's a CFT without stress tensor because it is non-local. So, or if you wish, again, using just simple terminology, you start from generalized free field and you add interaction. Okay. So this is what we do. So this is the model very much reminiscent of what I showed you before. So except that the local interaction is replaced by non-local term like that. So you have now two fields. Phi is ON, and here for just to make it a little bit different from the previous story, I put here just single field here, single O sigma. It's not a vector field, it's O1 field. So here the action is invariant under ON because it's phi is vector field, and sigma, since it's just a scalar, so it is invariant under sigma goes to minus sigma. So this is a Z2 symmetry. So you have ON cross Z2. But again, you can also promote it to two vector fields and study it continuous symmetry. So in the same way as before. So now what is nice is that you can play with this eta here. You can adjust it the way you wish. And in particular, can adjust it to such close. You see, if you take eta, so the scaling them before and you turn on interactions, the scaling dimension of the fields, because it's a Gaussian theory, just engineering dimension. You just calculate, just the scaling dimension is the same as engineering dimension because it's a Gaussian theory. So these are the deltas of two fields. This is how they look like. And you see that if you take etas, these etas to be close to d over 2, say it's exactly d over 2. If it's exactly d over 2, so you get d minus d over 2, so it's d over 2 over 2, it's d over 4. And since it's d over 4, it means that quartic interaction, phi to the 4 or sigma to the 4, will be d. Classically, it will be marginal. So therefore, if you take this etas, and this is something that you can adjust as long as you satisfy unitarity bound, etc. So you can adjust it to any values that you wish. So you can take it to be close to d over 2. And in that case, these 5 to the 4 operators become weakly relevant. So if you take the epsilons to be 0, these quartic interactions are classically marginal. But if you take this epsilon to be small and non-zero, these classically marginal operators become weakly relevant. And this is precisely what the Wilson-Fisher achieved by shifting away from d equals 3, shifting a little bit below 3 dimensions. Here, you keep dimension that you wish. You can take it 3, you can take it 3.5. You can take whatever you wish. You fix the dimension and you play with these etas here. It's not related to dimension. And if you take this eta to be close to d over 2, you engineer a weakly relevant operator. And as usual, once you have a weakly relevant operator, your flow from the Gaussian fixed point does not take you too far away. Okay, so you find an IR fixed point close to your Gaussian theory. So this is what we did. By we, I mean Ritam, Mikhail Goichman, Noam Hai, and Anatoly Demarsky. So this is what we studied. We started from a Gaussian theory, and we deformed it by weakly relevant operator. In that case, this is what it is. These are 3 weakly relevant operators. In that case, the calculation of the beta functions is pretty much standard. You just calculate this one loop diagrams, like in the Wilson-Fisher again. So the quadratic term is proportional to the OPE coefficients. This is as usual. So you calculate, just straightforward calculation. You find 3 beta functions, then you set them to 0. You get 3 equations, and you can analyze. This is for any n, not necessarily n is not necessarily large, just any n. So you get all kinds of fixed points. All these fixed points are stable, and it can be shown or proved that stability is guaranteed as long as fixed points satisfy these equations. So in other words, as long as fixed points satisfy these equations, determinant of the coupling of the matrix of couplings is positive definite. Everything is good. So all fixed points are good. So you analyze now. You just find the solutions. So you find the solutions, and again there are solutions with negative. So here the mixing between 2 sectors is O2. So G2, the coupling G2 is responsible for the mixing, for the coupling between the 2 fields, phi and sigma. So you find fixed points with negative G2, and you can calculate. Now you can also do calculation of the effective potential for the 0 mode in your theory at finite temperature. So at 0 temperature, forget about these pieces. So forget about m phi and m sigma. At 0 temperature, you get to leading order in epsilon, you get just quartic potential. This is your potential at 0 temperature. Now, once you turn on temperature, there are induced quadratic terms like that. Okay, and the masses, these are not actually masses because fields phi and sigma do not have canonical dimension. So these quadratic terms, so these are the expressions for these quadratic terms. It's just again simple one loop calculation. In this case, it's just this diagram. That's it. This is what you calculate at finite temperature. That's it. Very straightforward, simple calculation. And these are the masses that you get. Again, at 0 temperature, this loop is 0, so you get just quartic potential. But at finite temperature, because of Matsubara, blah blah blah, you get non-zero quadratic terms. Okay, and now, of course, the question is what are G1, G2, and G3? But you can actually calculate. So you can calculate this G1 and G2 and G3 from the fixed point equations. I mean, from here, you evaluate them. Again, you can evaluate it numerically. Mathematica speeds of the answer within seconds. So you can you evaluate them, and it turns out that if n is the rank of the orthogonal group, so if n is greater than 10, the coupling G2, there are fixed points with negative G2 couples between the two sectors. And if you increase n above 17, then actually quadratic terms are not positive definite. The mass of the sigma field becomes negative. Okay, and since it becomes negative, okay, so that means your zero mode, the true value of the zero mode is not zero, and therefore the symmetry is broken. So this is the symmetry breaking pattern. On cross Z2, this is the original pattern, at zero temperature breaks to On. So Z2 is broken. So now high order perturbative corrections will not change anything. So you can calculate high orders will not change anything. Why? Because close to the origin, you have, you have to account for only quadratic terms because they dominate close to phi equals sigma equals 0. They dominate. You don't care about phi to the 4, phi to the 6. All these extra pieces just are completely irrelevant. So, but, and therefore high order terms, high order corrections to phi square and sigma square will have necessarily higher power of epsilon, and therefore they will be subdominant. So therefore high order corrections in epsilon, as long as epsilon is small, and this is small by definition, it will not change it. So so therefore it will remain. So therefore it just illustrates that symmetry in this model, it is non-local, but it is unitary. It's a CFT, so it's UV complete, relativistic in the sense that it respects full Euclidean group, and it breaks symmetry at finite temperature. So large N analysis can be also done in this model, and similar to the previous case, one finds conformal manifold, moduli space of vacuum, and 1 over n corrections completely remove all these features or artifacts, depends on your standards. So I will skip because I think we discussed a lot, so I don't want to bother you too much. I will only mention one point, because you can always ask the question, who cares about all this symmetry breaking? Well, it's interesting to understand, but who cares? So what's physics? What kind of interesting physics you can engineer, even if you can break, for instance, discrete symmetries in a local model in 3 dimensions, in 2 + 1 dimensions? What kind of physics? So, so the claim is that you can have a thermally induced quantum Hall effect. So let me just explain it in simple terms. So imagine that you have a model which breaks in 2 + 1 dimensions that breaks parity. It should be local, okay? Because I don't know how to gauge non-local series. So it's a local model, local, unitary, UV complete, blah blah, CFT if you wish, that breaks parity in 2 + 1 dimensions. In that case, if you gauge this local model, because local models we know how to gauge. If you gauge it, it means that at 0 temperature, parity is respected, and therefore Chern-Simons term is protected. It will not show up. But if parity is broken at finite temperature, it means that you will get induced Chern-Simons term, induced by temperature. And as we know, Chern-Simons term is responsible for the Hall conductivity, and therefore I call it the thermally induced quantum Hall effect. So in other words, you would be able to claim that in a certain class of models, you have thermal effects generate Chern-Simons, generate Hall conductivity. Okay. So let me finish here. It was a bit too long. I apologize.
Thank you very much, Visha.
You were too polite not to stop me, so I really appreciate it, and I'm sorry for bothering you for so long.
No. Thanks a lot. Thanks again for a wonderful talk. Let's all applaud, unmute and applaud. Are there more questions?
Yeah, I have a question. Like your entire thing was dependent upon the formation of the hyperbola, which came because of the fact that you had different ranks. I mean, you had m and n minus m, and that therefore you had essentially the hyperbola coming in, right?
That's right. In the large n models, that's true. Because the model that I discussed.
Yeah. So, but that is kind of. Yeah. So, but that is not very generic. I mean, this is something that happens for these specific kinds of models. So can you devise some model where, can you devise some generic sort of model where the symmetry breaking takes place at finite temperature without this kind of, because if you have this seems to be completely an artifact of the fact that you have different ranks and nothing else.
That's right. So look, if you, for instance, in this last example, right, where you start from this model, right? Where is it? This model, right? You have a Gaussian model and you deform it by quartic interactions. In this case, you see the whole analysis does not rest on large n. So no large n. You can take n whatever you wish, except that if n is sufficiently small, then you will not observe this phenomena of persistent breaking, okay, of symmetry. But here again, the analysis does not rest on any conformal manifold, on any flat direction at finite temperature, blah, all these artifacts, let's call them. So here it just you just have the reason why you probably could engineer such a situation is that your symmetry group was sufficiently rich. Sufficiently, you had two groups, okay, ON and Z2 in this case. And you had enough couplings, you had like G1, G2, G3, and therefore you had enough fixed points. Because usually you have just one function, one fixed point, one single group, and somehow you don't have freedom to engineer such a thing. Here, it's because you had enough parameters, you could cook it up. So it's true that in the large n model, all this phenomena is accompanied by conformal manifolds and flat directions at finite temperature, or if you wish, moduli space of vacua. Indeed, this is the case, but I don't know if this is always, if it's a kind of must to observe symmetry breaking at finite temperature. So it just so happens that in these examples, this is what was crucial. But again, it's not necessary, okay? Because you can take finite n models, and this is the model that I show you here. It's a finite n model, no large n, don't take n to be large, and just analyze it, and you will find that you have the masses that are induced at finite temperatures can become negative. Quadratic terms become negative. Again, why they become negative? Because you had enough couplings, you had enough beta functions, and you had enough fixed points, or you wish special fixed points with negative, where one of the couplings, G2 in this case, is negative. So you had enough freedom to do this phenomenology, if you wish.
Yeah. So the point is that in models where the mass terms become negative at finite temperature are the kind of generic models in which this sort of thing happens.
Correct. Okay. But it's not easy to engineer. That's you see in simple models. If you don't have enough couplings, you will get always positive masses and therefore symmetry restoration. Or if you wish, the symmetry will not be broken. So,
one question: how clear is it in this last model, the long-range Ising defined by these quartic interactions, that the fixed point is a unitary CFT?
Okay, I'll tell you. So how to show unitarity? You basically have to calculate scaling dimensions, right?
That's one thing.
Right. So this is what we did. It's not like we have a proof that this is a unitary model. Okay. We don't have
because the one ascent operators that you were talking about with Richkow, there also the dimensions are not a problem. It's the OP coefficients that are a problem.
That's right. But we are seeking. You see, his construction will not be relevant here because his operators will vanish identically because we sit in 2+1. So therefore, his construction does not work.
Yeah,
now,
not exactly that. Yeah, I agree.
Right, and scaling dimensions. So we calculated various scaling dimensions, not all of them, but you know, you could in principle say calculate scaling dimension. Maybe one of them is complex, and that's it. End of story. So we calculated a bunch of them, and all of them were above unitarity bound and real. So therefore, we have kind of evidence, call it strong or not, that the model is unitary, but we don't have a proof.
I see. But could one not argue something like, you know, you start with a UV fixed point which is unitary because it's just long range Ising model, and then you deform it. So why should this go away? Why should that property go away in the infrared? I mean, something along these lines, basically. That.
Well, I agree. For me, I think it should be fine, but I guess it depends on how picky you are, right? I don't know. I don't. Is there a theorem that states that if you start from a unitary theory and you deform it, then you necessarily flow to unitary theory? So there is no way to break unitarity on the way.
That's what I was thinking, but maybe.
I just.
Yeah.
Okay.
Could I ask, following up on that, the original starting point, this long range Ising model, is it clear that that is unitary?
Yeah, because you see, it's a Gaussian theory. So you have to check if that is the scaling dimension of your scalar operator is above unitarity bound, right? And,
but I was wondering, like Abhijit, whether that was sufficient to establish unitarity.
So I think it should be sufficient, right? It's a very.
I mean, sorry. So you write down the Hamiltonian, right? An explicit Hamiltonian, long range Hamiltonian, which is a unitary operator. So this isn't it? I mean, at the level of the lattice, it is a unitary model, right?
Wait, does your model break Lorentz invariance?
Lorentz, well,
if here long range in space, then it's also long range in time if it's Lorentz invariant, right?
Yes.
So how would you write down this Hamiltonian then?
The Hamiltonian for the theory. I mean, for the in the continuum limit.
Yeah, if you take a model which is long range in space but local in time, then I think it's clear it's unitary, but it's not Lorentz invariant.
So you see, so this is the lattice Hamiltonian, right? So I think that the action here, when you write action in the continuum limit, that actually beta h.
I see. Sorry, I didn't quite understand that. This ddx includes time as well, right?
Sorry, which one axis?
When you write ddx and ddy, that the integral runs also over time, right?
Yes, right. That's Euclidean, right?
Right. So then this is a model in which something at one time is interacting directly with something at another time over long distances. I can't see at all that there's a Hamiltonian structure.
Oh, I thought this dd, that d there is a space direction only. That's what I thought.
You mean here, this d?
Yeah.
This is the same d like here. This is a space, right?
That's space, right?
That's space. So then your model is not Lorentz invariant?
No, I don't think so because, yeah.
Fine. Okay, fine. If that's fine. Yes. Yes.
But then does this mean that the resulting CFT is unitary?
But non-Lorentz invariant CFT.
Yeah.
Well, again, I don't even know. Well, I don't. Again.
I mean, at the level of reflection positivity of the space, like just static.
I don't. Let's say it that way. I don't know how to about this model in the real space, right? If it's not.
Thought that this was a finite temperature theory and the time was replaced by beta, right?
Right. So finite. When I say finite temperature, it means that I just put this theory on the cylinder.
Precisely, yeah.
This is what I mean. Well, again, it's in the same way, like in the case of generalized free field, right? This is the same story. You just how do you think about it at finite temperature? You just put it on a cylinder. This is how we think about it. So, in other words, so there is a kind of motivation from this long range Ising, etc. But
I see. So it's not that you actually take the Ising model and heat it up. I mean, you don't take the lattice system and heat it up, right? Because that time would be different, wouldn't it? That's a different time. That's not long range in that sense. But when you put this particular Euclidean theory on a circle of size beta, that's like, I think, you know, that the time is taken to be this long range time. I mean, this space direction is becoming time. Right?
Yeah, right.
So it's not okay. You won't be able to see this in the lab. Then, if you have lattices which interact long range, because then, you know, to do this because it's a funny temperature, in other words, isn't it? I mean, I may be mistaken, but maybe you should correct me.
You mean again, if you take you're asking the fault. So this is a Hamiltonian, right? So in principle, the statistical sum is clear. It's e to power minus beta times energies of this Hamiltonian, right?
Yes.
So now I want to just write down the path integral representation for this statistical sum for this Hamiltonian
At finite temperature.
Finite temperature, right? So
yeah.
I calculate e to power minus beta h.
Yes.
So I claim that e to power minus beta h for this Hamiltonian, and you have this energies of this Hamiltonian, e to power minus beta h. I substitute this calculation by the path integral, where the action, where, you know, I use this periodicity condition, because, you know, the claim that you have this periodic boundary condition is independent of the path integral raising. So in other words, it's just a you know, KMS. So in other words, it's a mass that you have to calculate partition function for this kind of Hamiltonian. You have to put your theory on a cylinder.
No, but sorry. I mean, when you say e to the beta h of this long range model, that beta is a different circle, right? That's a different circle. That's not one of these d directions, is it? Because but the other thing that you do, where you take one of these d directions and then compactify it, that's like this long range time also, which Raz was alluding to, non-local time, and that seems a bit different kind of a temperature. So that's why I was saying that if you were to actually heat this up, that doesn't look like taking this theory and taking it one of the direction to be compact.
That's not clear to me, because again, when you take, let's again talk about generalized free field. When you calculate thermal correlation function in the case of generalized free field, that's precisely what you do, right? You just compactify one of the directions. This is how you calculate it.
Maybe what Abhijit is asking is whether D includes the beta direction.
Yeah, this is again. Yeah, this is what I'm trying to say. That again, I mean, the 2-point function for the, you know what? You don't even need an action for this case. You have let's just let me share the screen. So you have, say you have a correlator like that, x minus y to power 2 delta. This is for your generalized free field. This is a 2-point correlation function. Phi of x, phi of y, right? This is for the generalized free field. This is D. I sit in Euclidean dimensions. So you have this phi of x, phi of y over x minus y, So here you have also ddy, generalized field, so it's 2d minus 2 delta, right? So this is your correlation function with some number, it doesn't matter, say it 1, okay? Now, if you want to write down a thermal correlator without even asking how the action, Euclidean action looks like at blah, 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 thermal cylinder, you want to, just from this correlation function, you want to get a thermal correlation function. How do you do it? I thought that what you do, since it should respect periodic boundary conditions. So what you do, you just do method of images, right?
Yeah, but here you are assuming, there is no lab here, right? I mean, here you are assuming that just the time is one of these directions. It's just Euclidean one that you have written.
That's right.
So then, in other words, this Euclidean invariance here is analytic continuation of this underlying Lorentzian invariance of the theory. So indeed, in particular, this has some non-locality in time also, and then you can put this. That's what I was thinking. That is the difference.
Yeah, but otherwise, so I just want to understand. So how would you, again, if you have such a generalized free field, how would you couple it to the other beta that you have in mind?
Well, so I think as you said, this generalized free field maybe can be thought of as this long-range Ising model, right? Can be thought of as a long-range Ising model, and then I would take that model there, and then put that on as a statistical model, and then put that on the finite temperature, right? Adding an extra dimension, and then I don't know how to take the low energy limit, how that would look like, but it would probably look a bit different because
and would violate Lorentz invariance naively.
Yeah, because of space direction interacts long range, but in the time it's just the IHT evolution.
But eventually, what's your the correlation function, thermal correlation function? I think you can always reconstruct, especially in the case of free field, you can just from the zero temperature.
When there is Lorentz invariance, right?
Right. You mean that in this case you would say that you do not have Lorentz invariance
because there is a different time direction, a separate time.
Yeah. In that case, right? Right.
Okay. Okay, I don't have any other comments, but if anyone else has any questions or comments. Okay, if not, let's thank Misha again for a wonderful talk.
Thank you so much, Misha.
Thank you.
Thank you. Okay.
See you.
Bye.
Bye.